Today's lecture topic will be about regularization and optimization, which are two very important concepts more broadly in deep learning and machine learning, but especially important for computer vision. And we're going to start with a recap from last week and discuss some of the topics that we discussed last time. So we really honed in on this idea of image classification as a core task in computer vision. And what this task is given an image as input, you try to map this image to a label inside of a set of labels. So here we have 5 different labels, cat, dog, bird, deer, and truck. And the goal is to assign the correct label to the input image. And you're creating some model or some function that takes an image as input and outputs the specific label here. And we also talked about, a lot of the challenges for classification. So one of the main challenges is shown in the top left here, but it's this idea of the semantic gap between what we as humans perceive in the image, which is the cat, and what it's actually represented as in the computer, which is this grid of pixel values, where you have this multi-dimensional array or tensor, and you have discrete values for each of the pixels. This is very different from how we're perceiving the image and just deciding that this is a cat. So being able to map from this complex numeric representation into one that we humans understand is the core challenge here. But also there's challenges surrounding the images themselves. So if you look at something like the illumination of the scene, so here you'll have different pixel intensities based on where the lighting is in the scene. Also, you could have certain parts of your object are in the shade and harder to see. Cats, by nature, are very deformable. So you talk about deformable objects, they can move around and twist and bend in different ways, so they won't always have the same shape. And this can prove challenging if you're trying to design an algorithm to detect objects. There's also the challenge of occlusion. So you could have a cat that's like hiding underneath the couch cushions here, but we as a human can clearly tell this is a cat because of the tail, how it's sort of sticking up at the end here, and then, the way that cats behave, we can infer that this is a cat. You'll also have things like background clutter where the object could blend into the background. So we need to account for this somehow as well. And finally, there's this idea of inter-class variation where different objects in the same category can look very different from each other, but we still need to group them all into the same category. So here are a lot of just the challenges of recognition and why it isn't such a simple problem where you can just sort of write if-else rules to account for everything and just simple logic to classify. So if logic's sort of thrown out the window, you can't just create these logic rules. How do you actually create a classifier? Here's where we talked about data-driven approaches. And we talked about basically the simplest machine learning model, which is this k nearest neighbors model. And the idea is that you look at, for a given data point, what are the existing data points in your training set that are very close in distance to your new data point coming in. And for the one nearest neighbor case, this just results in, you find the closest data point, you assign it that class label. And you can also look at multiple nearest neighbors where you're assigning the most common class label among those nearest neighbors. So we talked about these two different approaches. We talked about how you ideally don't want to split your data set into train and test, but you can do train, validation, and test so that you can use this validation set here to actually help you choose your hyperparameters. So the main hyperparameter for k nearest neighbors is this k, 1 or 5 in these examples. And what we showed is an example where you're plotting what is your accuracy on this validation set here over the different k values here, and you would choose the one that has the highest accuracy. So this is how you'd use the validation set, and then you would reserve this test set for, okay, how does your model do on completely new data it's never seen before? That would be the purpose of the test set. This is all just recap. There was a bit of confusion about distance metrics. We put a post on Ed that explains this in more detail. But we talked about 2 different distance metrics, the most 2 commonly used ones in machine learning, which are the sort of Manhattan distance and or L1 distance and L2 distance or Euclidean distance. L2 distance is like if you imagine just the straight line distance, sort of how we think of distance in everyday usage of the word. Geometrically. And then Manhattan distance is this idea where you can only sort of traverse left and right and up and down in this diagram, and you can't move diagonally. So specifically looking at just one quick example here, the reason why all these points on the line are the same distance from the origin here is because you can't move diagonally, so you have to move in this case, up 0.5 and to the right 0.5. So the total distance is 1, whereas, here you're just going in a straight line, but it's 1 also. It's the same distance here. Whereas in the L2 distance, all the points equidistant from the origin here form a circle because you can just go in the direct line here. So this is maybe a brief explanation. The final thing we sort of honed in on last time was this idea of a linear classifier. So the basic idea in the basic setting that we did is we have an image which is, say width 32 and height 32, and there are 3 pixel values for each of the spatial locations in our image representing the red, green, and blue intensities, forming the color. And the idea is we take this array of numbers for our image and we flatten it out into an array of just 3,000 different numbers, 3,072. And then we're multiplying this vector by our weight matrix W. And the basic idea is if we have a weight matrix W that has, height here of 10, and then the width is 3,072, we're multiplying each of these rows by our input sample X, and this will give us 10 resulting class scores. So oftentimes we'll add a bias term as well, which would just be 1 bias term for each class. So this would be, a size 10 vector here. And we also talked about 3 different ways you can view or think about these linear models. One is the algebraic viewpoint, which I described here, where each row is represented sort of independently representing the class, and you multiply it by the input vector X, you get your score, and you add the bias to get your final score. And you do each row sort of independently in this sense. You can also view these learned class weights here as templates, where if we then sort of re-ravel the vector into the original shape of the image, we could plot the intensities here and understand what is sort of the template per class, which is what this visualization represents. And then the final way you can think about it is in a sort of geometric viewpoint, where each of these rows in our weight matrix are represented by these lines here in our input space. And specifically, the line is where we set this equation to 0, which is the decision boundary. So this forms the point where, above the line you could have a positive score, and below the line you would have a negative score for the class. So these are sort of the different viewpoints for how you can view these linear models. They're all doing the same thing. And one nice thing about the geometric viewpoint is that if you visualize your data, like say you want to classify blue versus red here, it's very easy to tell that you can't draw a line that perfectly separates the data here. So it's kind of a nice way you can gain intuition about what is possible for a linear model to do. Okay. I think that's sort of the high-level recap of what we discussed last time. I'll actually be going into a little bit more detail on sort of the new content for this lecture now, but I just wanted to pause briefly. If anyone had any questions about what we discussed last time or at the beginning of this lecture, feel free to ask. Yeah, so the question for those online is, for this visual viewpoint, is this the same as sort of running k nearest neighbors, and this would be maybe one of the neighbors that you're comparing against? Are they mathematically equivalent? No, they're not the same, because these templates are formed from this line, so it's not like one specific data point. But you can still calculate the templates based on the this sort of they would represent more like if we see in this diagram here, there's the line pointing in the direction of the class, so it would be sort of representing this point here. Yeah, so the question is, how did we get this like 3072 number? So the idea here is that if the height of our image is 32 pixels and the width is 32 pixels, and then each location in the image is represented by 3 values, the red, green, and blue pixel intensities, we would then get 32 times 32 times 3 total values to represent the entire image, and that's how we get this 3072 number. So here's a, I guess, very specific example of a linear model here. And when we multiply our input X by our weight matrix W, we get the resulting scores for these different classes. And you can see that for cat, it's not doing so well because car has a higher score and we want the highest score for the correct class. Also, here on the second example does pretty well because it's doing it correctly. But then in the frog example, it sort of gets it completely wrong, where it's by far the lowest score of the three. So intuitively, we can tell that these scores are not very good. But how do we sort of mathematically formalize this intuition? And how do we determine how good a given model is? And this is the idea of a loss function, which tells you how good, or specifically tells you how bad a classifier is. So given a data set of examples, where we're indexing with this letter I, we have X, I is each of the training examples, YI is each of the training labels. We can compute the loss over our entire data set, where we calculate this loss for each training example by sending it through our model here, which is this f of xi w. We get our label, and then we compute it compared to the ground truth label yi, and we just take the average over our whole data set. So this is how we do this. We talked about in last lecture the softmax loss, or the cross entropy loss, which is the most commonly used loss for classification. And so I won't discuss that again in so much detail here, but basically it's very high. It's very high loss when you predict low probability of the correct class. It's very low loss when you're predicting the correct class at very high probability. So this what I just explained is all contained within what we call the data loss. So this is a loss that tells you how well do the model predictions match our training data. And obviously we want this to be very low. And if it's very low, it means our model's fitting our training data well. But there's a second component, which I'll discuss today, which is this regularization term of the loss function. So what this does is it's intended to prevent the model from doing too well on the training data. So it actually does worse on the training data, but the goal is to make it do better on new test data or unseen data. So worse on training, but better on a test set. That's the point of regularization. And we'll go over a lot of the intuition for how to think about it in the next slides here. But the high level goal is to do worse on the training data, but then better on the test data or just unseen data. That's the point of regularization. Yeah, so we're computing the loss on each of the I training examples. Yeah, so the loss of the ith example uses the xi and the yi. Does that make sense? I mean, you could not have an I here, but this is just saying the ith loss term. Yeah. Yeah, you normally don't have a different loss for each I, if that's what you're asking. Yeah. So it's just we described Li as the loss for the ith training example, so we're just using it here, but yeah, it could be L. So for regularization, people usually have this intuition when thinking about it, where this is sort of like a toy example, and the idea is we want to fit some function to these points, where our input is x and our output is y. And you say have two different types of models, F1 and F2. And you're trying to decide which of these is better. So F1 goes through all of our data points. So the training or the data loss will be very low because it's basically doing it perfectly. Whereas F2 doesn't go through every point perfectly. But intuitively, it feels like probably F2 is a better model when we're now testing on new data we've never seen before. So regularization sort of captures this intuition of you don't want to overfit your data so hard, and you might actually be better off with a model that fits the data less, but is either simpler or has some other properties that make it a better choice. And so if we ask, okay, how are these models going to do on new data that's within our same distribution, you'll find that F2 does a much better job at modeling. So here's it's doing better on the unseen data. So I think there's also an intuition in this previous example that's demonstrated very well, where we're preferring simpler models, where it's sort of like Occam's razor, which is this idea in philosophy and also scientific discovery, where if you have multiple competing hypotheses, you should go with the simplest one first, and then if you know for sure that's wrong, then you can start trying out more complicated ones as you go. But this is maybe also some intuition you can have for why regularization can be useful. Okay, and then one final thing about this equation that I didn't touch on yet is this lambda parameter here. So this is the regularization strength, which is another hyperparameter. So we might use training and validation sets to set what is the optimal lambda here as well. But the basic idea is we can set this to a floating point between, I guess, 0 and infinity, where 0 would be basically there is no regularization. Infinity, up to infinity, you have a really strong, a progressively stronger regularization. So it's very much a tunable knob you have for determining how much you want to prevent the model from fitting to your training data. And I'll go through some simple examples now of regularization. So here we have L2 regularization, which basically what you do is you have your weight matrix, you square each of the terms in your weight matrix, and then you sum them all together. And that gives you your score here that you then multiply by lambda and you add to your total loss. That's L2 regularization. L1 regularization is very similar, but instead of squaring, you're taking the absolute value. So in practice, there are some differences between how these two regularizations perform when you're training models. So one of the things that happens with L2 regularization, because you're squaring each of the values, when you have a really small value, it gets squared, like say you have 0.001, you square it, it becomes even smaller. So L2 regularization allows for sort of these really small values close to 0, because you then square them so they become even smaller, and so your penalty here is very low if you have these very small values with L2, whereas L1 you're not squaring it. So it's sort of just whatever the baseline value was. It's not like it's getting smaller before you're computing this regularization term. So in practice, what this leads to is L1 regularization, you get a lot more values that are 0 actually in your weight matrix, or very close to 0, whereas L2, you can have, generally it's more spread out, where you have values that are small but non-zero, because the penalty becomes so small. Seems pretty clear to you why L2 prefers sort of spread out weights that are all small, but why does L1 prefer sparse vectors? So I think the way to think of it is that if a value can be 0 and your performance is roughly the same, then this would push you towards zeroing that value. Whereas for L2, what you might have is the value just becomes very small but non-zero because of the squaring. So the question is, we talk about what does pushing towards a 0 value mean? So we're going to talk about more how we use this loss term, but the basic idea is we're trying to minimize it. So we're trying to minimize the loss or minimize the error of our model. And if we have a term here which is giving us positive values that it's sort of not affecting the model performance and the data loss, we will sort of remove those through the optimization procedure. It's sort of a trade-off. You're trying to optimize the joint sum of the regularization term and the data loss term. So if your data loss isn't changing much, but you're able to go lower on the regularization term, you'll get a more optimized model. So it will be preferred based on trying to minimize the overall term. I think we'll also touch later in the course about much more complex forms of regularization, where they're all doing this basic idea of worse on the training data to do better on the test data. But some of them you will even change the layers of your model. So they actually get pretty complicated. This is like an ongoing research area of how to regularize models. There's new papers each year, so lots of stuff here. We'll only cover a small subset in this course. So to summarize, why do we regularize models? The first is, it allows us to express some sort of preference over weights. So if for some reason in our problem we think the solution should be spread out or should contain a lot of sparsity where a lot of the values in the weight matrix are 0, we might prefer one set of regularization, L2 versus L1, over another. It also can, depending on how we're regularizing, make the model simpler so that it works better on test data. So it could simplify the model if we're, say, heavily regularizing really high polynomial terms in our model, for example, in what I showed earlier. Or something we won't touch on in too much detail is especially L2 regularization can actually improve the optimization process, because if you imagine the squared is like a parabola, so if you're plotting y equals x squared, it's a parabola, and these are convex, so you get a lot of nice optimization properties where there's a global minimum. We won't touch on that in this course, that's beyond the scope, but know that for certain types of optimization, the regularization actually helps train the model faster too. Okay, I guess I have a question for you all, and what we'll do is you'll do 1 if it's W1 and 2 with your hand if it's W2. So which of these two weights, W1 and W2, would the L2 regularizer prefer? So we have our input X, it's when you multiply it, you do the dot product with the weights, you get the same score. So you get a score of 1 either way. And here's where the data loss would be the same. And we're trying to determine which of the weights would our regularizer prefer. So go 1 if you think it's W1 and go 2 if you think it's W2. All right, lots of 2s. Yeah, it's W2 because, as we said, it's more spread out. You're going to be squaring each of these terms, so it's 1/4. You square it, becomes 1/16. You sum it all together, it's 1/4 is the total regularization term here, and then here it's, you square it, so it's 1. So it's 4 times lower in terms of the regularization loss. And as we said, the intuition is you like more spread out weights. And then here's another question. Which one would L1 prefer now? So you do 1 if it's weight 1 and 2 if it's weight 2. Okay, we got a lot of 1s. So this one's actually a bit of a trick question. So what L1 regularization is, you sum each of the terms, so they'll both be summed to 1. In practice, you probably would see this one because, as we said, the sparsity. But in terms of a loss standpoint, these two weights would actually be equivalent in terms of L1 because one is just the sum of these 0.25 4 times, and then the other one is just 1. So they're both summed to 1, and so the actual regularization term is the same for these. Yeah, okay, so what's an example where L1 would be preferred? If this is like 0.9, for example. Okay, so just to recap, we have a data set of XY pairs, and we have some way to calculate scores for each of the classes, which in our case is just a linear model. You're doing a matrix multiply. The loss for each of the I training examples in the softmax loss, which we discussed last time, is you exponentiate each of your scores, and then you divide by the total sum of the scores. So you exponentiate to make them all positive, and then you sum to get a probability distribution. So they all, the final values in this all sum to 1, and you have a score for each class, and you take the minus log of the correct label. So this is of the probability of the correct label, which is given here. And the full loss is you just run this over each of your training examples, calculate LI for each of those, and then you add your regularization term here, depending on what is the weights of your model. Why do we use softmax in general? So softmax is great because what it does as a function is it converts any set of floating point numbers into a probability distribution where they will sum to 1. And depending on the value of the score, that will translate to the relative probability of that value. So if you have a really high positive number and everything else is very low negative, you'll have nearly 1 for softmax and 0s almost for the other values. So it's nice because it converts any list of floating point numbers into a list of probabilities based on the values of the list. That's the main utility of softmax. So the question is that you can view the regularization we talked about, which is L1, L2, as a way of regularizing based on the magnitude of the weights, which is true. And how does that translate to simpler models? So I think in L1's explanation is actually pretty simple because if we prefer, say, terms that have a lot of zeros in it, it's basically a linear model with fewer coefficients. So that one is actually, I think, relatively straightforward. But I think in general, regularization is not always going to give you a simpler model. It depends on how it's used. So for example, in the diagram we showed at the very beginning here, here you could imagine that you have L2 regularization or L1 regularization where you're penalizing more the higher degree polynomial terms of your function. So in that sense, it's pretty clear how you could design regularization to prefer a simpler model. But it doesn't always need to be that way. Really what it is this idea of doing worse on the training data to do better on the test data. And that's not always going to give you a simpler model. And in fact, there are many types of regularization like dropout that actually make your model more complex, but give you better performance on the test data. Cool. So now that we've talked about how we can calculate how good a given W is based on the training data and this regularization term, the question now is like, how do we actually find the best W? And this is what optimization is, which is the second half of today's lecture. So I think when people describe optimization, they will usually use this idea of a loss landscape, which you can think of as like a normal landscape like on planet Earth, where the up and down vertical or z-axis direction is the loss. So this is the value you're trying to minimize. And then say in this example, you have two parameters in your model, which is sort of the X and Y direction of where you are in this landscape. And the idea is you're just like basically a person, you're walking around this landscape and you're trying to find what is the smallest or lowest point in the entire landscape. I think one of the reasons this analogy, and this is a very commonly used analogy, a little bit falls apart is because, as humans, we can just see, like visually, we can look into the distance and see what is the lowest point of the valley. But I think this analogy is actually pretty accurate if you think of the person as being blindfolded. They don't have access to any visual information. They can only feel sort of the earth where they are right now and understand what is the slope of the ground on the current point in which they're standing. And I think if you view it in that lens, this analogy actually becomes extremely accurate for how we're trying to find the best model, and we have this complex landscape of different loss values depending on the parameters of our model, which translate to the location of the person in this landscape. So how can you find the best point? We could go with like a really simple idea, which is maybe a really bad, bad idea, but it could work. So here it's just basically a for loop where we're trying 1,000 different values of W randomly, and we're just choosing the best one. So obviously not very mathematically rigorous, but you will do better than a random baseline. And if you had nothing else to go for, maybe this isn't so bad. You would get like 15.5% accuracy on the CIFAR 10 data set, which is the one I showed earlier with the frog and the car and things like that, with the 10 different categories. But it doesn't perform very good. I mean, the state of the art on this data set, it's basically solved through modern deep learning. You get 99.7% accuracy. So clearly it's not bad, but it's also, I wouldn't say, particularly good. Strategy number 2, which is sort of what I maybe explained a bit earlier, is this idea of following the slope. So for this, you can imagine you're like blindfolded on the lost landscape and you're feeling the ground underneath you. And you're thinking, okay, which way is the slope of the earth pointing me? And I should walk in that direction at all times. This basic idea is the fundamental way in which we train all the models in this course, and in which basically all deep learning models are trained, where you're feeling the location of the current place in the lost landscape and you're going down the hill. So this is a very intuitive way to explain it. We'll now go over more of the math behind it, but this is what you should be maybe visualizing in your head. So how do you actually follow the slope? So in one dimension, I'm sure you all are familiar with the idea of a derivative, which in calculus we can think of as this limit h definition, where we add a very small number to our current location. We calculate the value of the function at that new location. We subtract the current location, and then we divide by the step size. And as we take the limit for h approaching 0, this gives us the derivative of the function at that point. Now, this is for 1D, but in multiple dimensions, you use the gradient, which is where you're calculating essentially this limit definition for each of the values separately. So you have a different derivative for each of your values, and you get a vector instead. And this gives you the direction along each dimension. So you can actually calculate the slope in the dimension by taking the dot product of the gradient with the direction, and specifically the direction of the steepest descent, or down the hill, is the negative gradient. So the gradient points up the hill, the negative gradient points down the hill. So this is the direction we should be traveling if we're trying to get to the bottom of this lost landscape. So, maybe what are some ways you can calculate the derivative? A really simple one is you could just actually try to use the limit h definition with a very small h. So you add, 0.0001. You actually can compute, the last two digits of the loss change slightly, so you can compute the difference, divide by the step size, and you can get like an approximation of your derivative here. And you could actually do this for each of your values in your W. You just do this procedure over and over again. But it has a few problems. It's very slow because you just need to loop through each of the values. It's also approximate, so you're not even calculating the actual derivative, and especially with floating point arithmetic, you can get pretty significant errors here. So this is not really preferred, but this basic idea or intuition of what we could be doing is to calculate the derivative this way. But really, we have the loss as a function of W. So we know how to calculate the scores to calculate to get our loss, which is given by our function for our model. And we can then compute the total loss with the regularization terms as well. And this entire loss is a function of basically W's, the W's, the Xi's, and the Yi's. So you have your W matrix, you have your Xi's and Yi's, and then you have this formula with, maybe some logs and exponents. But fundamentally, this is a function of W, X, and Y. And we specifically want to calculate the gradient, which is given by this Greek letter nabla, of our loss with respect to the weights. So we can imagine our X and I, Xi and Yi's are held constant, and we're trying to calculate the derivative just with respect to the weights. So to do this, we can just use calculus, use the chain rule, use the different methods we've learned for calculating derivatives based on sort of complex equations, or not so complex, but you need to have some logs and exponents and chain rules here to solve it. So this will be an exercise in the homework, so I won't go through step by step how to do it now, but it is relatively straightforward. I think conceptually it should make sense to you all how you do this. You assume the X and the Y's are constant, then you solve for what is the derivative as you change W. So now we actually have a way where we can calculate W based on our dW, the gradient of W, with respect to our data and the current W and whatever our loss function is, which is how to compute the error. So this is, I guess, a summary. So you could do a numerical gradient, but it's approximate slow, and the nice thing is that it's very easy to write. You just add a really small h, take the difference, divide by h. The analytic gradient is nice because it's exact, it's fast, but you could potentially, if you're creating a new gradient from scratch, new code to calculate it from scratch, you could have an error in it. So if you are doing this, people normally will have a gradient check, which is where they try the h version, where they have a really small h value, and then they make sure that it's around the same neighborhood, and that's a good way to make sure you don't have any bugs in your code. You'll be there'll be gradient checks in your homework assignments to make sure your implementations are correct also. Yeah, so the question is, we often say we want a loss function that's differentiable, because then we can calculate the gradients. But if we have a better loss function somehow, and we can't analytically calculate the gradient, but we could use this H kind of numerical method, could we do that? I think in general, it's hard to construct a better loss function that would be non-differentiable. You could possibly though, and if there is just a true loss function that is the best for your case, but it is non-differentiable, you could go with this approach, and it may work. I think it would struggle if, for example, your loss is just truly non-differentiable across all points, and it's basically like a cluster of non-connected points. Then moving in the step of steepest descent wouldn't really get you necessarily at your best solution if they're not well connected and forming this geography. So it could work, but I would think that if your loss is non-differentiable across most of the domain, then probably you wouldn't be able to use these approaches to find the bottom point. Yeah. So I guess TLDR of the explanation is that if your function's convex, then it works very well with this sort of gradient descent or steepest descent type of approach. But if you have a non-differentiable, non-convex function, probably this approach won't work as well, because you're not going to be stepping in the right direction. It's not necessarily error prone if your code is perfectly good, but maybe you have a mistake in your code and it's hard to tell right away. But the limit h definition is very easy to code up, right? You just set h to be a very small value. You run it through your function and you add a very small amount. So that's less error prone for implementation.
Okay, that's
for implementation.
okay.
Not more error prone if it's working correctly. Okay, so now I'll talk about this fundamental algorithm for optimization called gradient descent. And the basic intuition is what we already explained before. We calculate the slope at each point when we're on our lost landscape, and we take a step in the direction downwards towards the bottom of the lost landscape. So what we do is we calculate the gradients of our weights given the loss function, the data, and our current weight values. This tells us how much we should change each of the weights to go down the slope. And then we have to have a step size. So how far down the hill are we taking a step in the direction? And so you go down the hill, so it's the minus sign here, and the step size times the gradient. So this is basically what gradient descent is. You're calculating the gradient at each step, and you're moving a fixed direction in the direction of the negative gradient down the hill. So given a concrete example here, so instead of this being like a 3D loss landscape, often people will visualize it like this, where we're sort of looking down at the landscape, and purple would represent the highest points and red would represent the bottom or the valley here. And we could imagine we have our original W, we can calculate the loss, we know the direction of the slope, the negative gradient direction, and this arrow might represent the fixed step size that we talked about before. We're taking a fixed step size in that direction. Yes, you can see it's fixed step size, but as the gradient becomes smaller, we're still multiplying it by this fixed step size, so the effective step size actually does become smaller because the gradient is smaller near the end where it's flat, or near the end where it's more flat. So this is what it looks like when we're always heading in the direction of the steepest descent. So the question is, when we step down, how do we know when we're going to stop? Well, I guess in this formula, right, like you just keep looping forever, so you never stop. So this was probably not the best. Normally you have a predetermined number of iterations that you run it for. Or you can look at if the loss is not significantly changing by a fixed amount also. You can have like a tolerance for how much you're expecting the loss to keep decreasing by, and if it's no longer decreasing, it's only decreasing by 1e minus 5 or 1e minus 9, maybe you stop there because it's good enough. So those are the two ways you can determine when to stop, is fixed number of iterations or a stopping criteria of, how much we're not really improving that much anymore. Okay. So now I'll talk about the sort of most popular variant of gradient descent, which is called stochastic gradient descent. And when we talked about gradient descent before, we talked about calculating the loss of our weights by summing over our entire training set, the loss of Li for each I in our entire N training sets. But this is like potentially a lot of computation if we have a very large data set. So what stochastic gradient descent is it basically now, instead of looking at the entire data set, we're looking at a subset each time, which we call a mini batch or a batch of data. And so here, if we look at the code, it's like, we're sampling 256 data points from our data set, so the batch size is 256. We evaluate the gradients of this 256 subset of our data set, and then we do the same thing as before. So the reason why it's called stochastic gradient descent is because we're sampling a random subset of our data set each time we're running the algorithm, each step of the algorithm. So this is stochastic gradient descent. You're basically running it on a random subset each time. And in practice, people won't just sample it completely random. They'll make sure to get through all the examples in their data set and then sort of loop around again. And that's called one epoch of training, where you loop through all your data samples once in a random order. Okay. There are some problems with gradient descent or stochastic gradient descent. So this visualization is sort of the same type as the colored one I showed before, where we're looking down the loss landscape, but these curves are called the level set, where it's a set of points where the loss is the same on all of them. So this is another way of visualizing, sort of very popular way to visualize top-down looking at the loss, but it's without the colors. And so you could imagine that you have this phenomenon where it's like a really narrow valley, where it's really steep along the sides, and you're trying to traverse the center of the valley. And, gradient descent actually does run into issues here. Does anyone have any ideas for what could go wrong? Yeah, so one of the things you could do is overshoot, where you're sort of moving up and down along this direction. And if it's steep enough and your step size is large enough, you might actually oscillate out of the valley. So you can imagine if your step size is very large and this is really steep, you're actually going to be gaining, like you're moving out and out each time, because you always have this fixed step size. So if it's steep enough, you could just like bounce out of the valley. That actually does happen if your learning rate is too large. So that's one thing that can happen. And then also, even if your learning rate's not too large or your step size is not too large, you can have this phenomenon where you're sort of jittering because the gradient is much larger in the steep direction. So you're sort of jittering, but you're not making very much meaningful progress towards the actual center because you're spending all this time oscillating back and forth, up and down. So this is a pretty big issue with just default SGD. And then mathematically, just an aside, the loss function we consider here to have a high condition number, which is the ratio of the largest to smallest singular value of the Hessian matrix, which is the second derivative. So you can imagine like the second derivative along this up and down direction is very high, but then side to side it's very low because it's very flat. So that's what causes this phenomenon. All right. So one of the things we also might have an issue with SGD is what happens if the loss function has a local minima or a saddle point. So for example, here for like just the very end of this curve, it's completely flat. So if we were to imagine there's like we're moving down the hill here, we would just get stuck here because it's flat, and we wouldn't be able to progress any further because when we take the gradient here is 0. So this is actually a pretty big issue where it'll get stuck either in a local minimum because once we reach here, we don't really have any direction to go. The gradient is 0, or it's very small, and we'll just sort of oscillate back and forth here. And then here it could actually get stuck on this bottom example because the gradient's 0 here, even though if it went a little bit further, it could go down significantly more. Yeah, so the question is, maybe we can change the way we're doing the steps. Maybe we could use the Hessian to determine the direction we go. We actually do have a brief slide talking about the sort of Hessian style approach at the very end. That's not very commonly used in deep learning, but the short answer is yes, there are going to be actually several ways in which you can account for this that we're going to go into in like 5 minutes. So it's a good question. Yeah. We'll get to that. Okay. I think one of the other things that you might not know is that empirically, saddle points are actually much more common as you move to higher dimensional models. So as your weight matrix gets larger and larger, you're more likely to find these saddle points. And there's this paper describing the frequency of them. If you don't know a saddle point, it's called a saddle point because it's shaped like a saddle, like on a horse. And at the center of this saddle, the gradient is actually 0 in all directions. So it's like the bottom of this and at the top of this sort of curvature. And so in both the x and the y directions, the gradient's 0. So you could get stuck here despite being very close to like going significantly down the loss landscape on either side. So this is also a pretty common issue with SGD, where these saddle points, and as we move to higher dimensional spaces, or this is equivalent to models with more parameters, this is more and more common. This is a big issue. And then a final issue with SGD is that we are sampling a subset of our data each time, right? So we're not looking at the whole, this represents the entire loss across all the data, but we're looking at just a subset each time. So we'll actually have somewhat noisy update steps because we're not looking at the entire data set. So we'll sort of be stepping towards the center, towards this sort of local minimum that we're trying to reach here, but each step doesn't go directly in that direction. So there's some noise in how we're progressing because we're subsampling the data set. Okay, cool. I think to summarize, these are the main issues, and there's a pretty neat trick you can do where you just basically add momentum, and you can really think of this as the same way as like if you have a ball that's rolling down the hill where it gains momentum. It's actually very similar to how it's modeled in terms of the physical properties. So it's a good way to gain intuition about it at the very least. So you can imagine that it could help with you have these local minimum, because if you're rolling down with enough velocity, you'll be able to come out of it. If you have the saddle points or the just flat point here, the model has been rolling down the entire hill, so it won't get stuck here anymore. It will continue. Also, if you have this poor conditioning value, you will still have maybe some oscillation, but the nice thing is that it will sort of accumulate speed in this direction to the right, because it will have multiple steps that keep going that way, so it'll gain faster and faster towards the center here. So it also helps with this problem. Finally, it can also help sort of average out some of the noise with the gradients, because they all sort of have a direction in common, which is towards this minimum here. And so as you're computing the momentum, it sort of builds on itself and it will converge faster, because it sort of, the noise is accounted for by looking at the direction they all share in common, which is included in the momentum. So let me show you how to actually do it, but this is sort of the general intuition for how momentum works. So we have SGD here. We have our mini batch X. We're computing the gradient, which is dx. We have the learning rate, or the step size, which we multiply, and then we do the negative because we need to go down the hill. This gives us our new X, so this is SGD. With momentum, we're now updating by this velocity term. So instead of updating by the gradient at the specific point, we're updating by the velocity. And the velocity at a given time step is given by the previous velocity plus the current slope. So this is sort of how you calculate it. And you have this rho value, which is the momentum, the actual, like how much momentum you want to have. And if you have it very high, then your new velocity is more dependent on the previous time steps velocity. And this sort of is a running average, therefore, of the last gradients depend, and the momentum term here gives you how much to weight the past versus the present. So now we're updating by this, and we still have this alpha, which is the step size. So it's actually a very simple change, right? You just are now computing the velocity, which is a function of the current velocity plus our gradient. So I think I'll pause for questions here. This is the explanation of momentum, and maybe I could also recap briefly how it resolves all these issues we saw. So, if now that you're adding momentum in the past, over the past gradient steps, you could see how it would keep continuing along this direction. And depending on your rho, if your momentum is very high, it would keep going and be able to account for a very large sort of hump here with the local minimum. Also, it's very good at sort of these saddle points because it will just continue along the direction in which it was going previously for a significant amount of time. And poor conditioning, if we're having cumulatively going to the right upon each step, the momentum will also be consistent there and build up. And then if we're oscillating significantly here, it will move less. It will move less in the direction because the values will cancel out in terms of the current direction and the velocity. They'll be pointing in the opposite direction, so it will get minimized. The question is, what happens if you're rolling like right along the saddle? I mean, I think in practice it's very unlikely, but in that case, yeah, you would just get stuck in the saddle. Yeah, I think that's like, your initial conditions, like wherever you start, is very unfortunate. So yeah, sometimes I guess that could happen, but it's very unlikely. Yeah, and it's also why in practice people won't run like a single model training run. Often they'll run multiple ones with different random seeds just in case something like that could happen. Another thing is, if you're doing stochastic gradient descent, you're much more likely to have at least a little bit of noise to get you out of like directly in that saddle back and forth. So I think it's basically it never would happen because of the randomness, but hypothetically I think that could occur. Yeah. So the question is, why is the saddle just an issue with SGD and not optimization in general? It would also be an issue with the entire data set. It might even be more common with the entire data set. So it's an issue that SGD faces, but it's also an issue that other optimization algorithms that just rely on gradient descent with no sort of bells and whistles attached would also, they would face the same thing. Yeah. Yeah, so the question is, does adding the momentum make it more difficult to converge because we'll overshoot and then, have to come back? I think the short answer is, yeah, it might not help with converging, but it will help you find, on average, it will help you find a better minimum point to converge to. So it will converge maybe more slowly because you won't get stuck in a local minimum. Like you would just converge here if there was no momentum, right? Versus overshooting. So I think a lot of this stuff is empirically shown where it's like it happens to be with the specific class of neural networks. The momentum does help training, but this is the intuition for why we prefer it. I think, to be honest, people will use whatever works best. And there are cases where people have found that stochastic gradient descent without momentum would outperform for a particular model. So here's the intuition about why it could perform better. But in practice, people will just try a bunch of different ones and see what works best. And I'm going over the most common ones that people try now. Yeah. But yeah, you're right. It could hurt convergence potentially.